In several physical systems, we might have variables that depend on time, and we are interested in studying the evolution of these variables with respect to time. So how these variables change in time. It's important, for example, to understand how the energy of a system changes. If the system is not non-conservative, then the time derivative of the Hamiltonian would be non-zero, for example. And if the system is a certain volume in space, so we have a three-dimensional volume, which might change in time. So the volume might differ from time to time. So if we analyze the system, how it evolves in time, this volume, the shape of the volume might change, for example. So for a fluid, but not necessarily a fluid. So we have a generic object, which is a volume, and then we can define some functions that characterize the physical system. So we might have a function, let's call it f, which depends on the position and might depend explicitly on time. And we might need to integrate the function over the volume. So this might represent some physical quantity. And in here we are interested in how to evaluate the time derivative of this object here. Now I will do it quite informally, but this should be a little bit more intuitive if you think of this in terms of multivariable calculus. So this dv, this differential of volume, might be also written as dx1, dx2, dx3. So it's the product of the three differentials. We have a system, a frame of reference, whose coordinates are x3, x1 here, which is the x-axis if you want, x2, x1, x2, x3. They might be also written as x, y, z if you want. And these are the three coordinates that we need in our three-dimensional space. Now, if the volume changes in time, not just the function, but also the volume, which means that the boundary of integration changes with respect to time. Or if you want, you can think that these small volumes change with respect to time. So quite informally, we can think that this integral is just a summation, and therefore we can apply the usual rules for derivatives. So for example, we have the derivative of a product, a times b, would be the derivative of a with respect to time times b plus a derivative of b with respect to time. And we can do something similar here. So we have the summation, so the integral in this case, of the derivative with respect to time of our variables, which are the function, but also the differential of the volume, dv. It also depends on time. So we have to think that the points here inside this volume can move, and therefore we have some kind of function x of t. So these coordinates x, we can think that they depend on time. Now we can also rewrite this integral as integral of the derivative of the function with respect to time times the volume, plus we have an integral of the function times the derivative of the volume. So let me write it as d over dt of dv. Now, the time derivative of the function, which depends on these variables and time, can be written by using the chain rule. So it will be the gradient of the function times the derivative of x with respect to t, plus we have the partial derivative of f with respect to time, because the function might depend explicitly on time as well. So this is how we can write this derivative, and we can write the derivative of this position with respect to time as the velocity, which we can think as the velocity of this generic point of the volume. The generic point has a velocity. And the derivative of the volume, what about the derivative with respect to time of dv, of this? Let's rewrite dv as the product of differentials, dx1, dx2, dx3. So you can think that these differentials here, these d's, are some increments in the variable x1. So we can exchange these increments with the derivative operator. So there is some kind of intuition here. It's not very formal because this is quite informal, But if you want to think of this more rigorously, you should discretize the integral. So therefore, in this case, instead of having the infinitesimals, you would have finite deltas, delta x1, delta x2, delta x3, and then after you do your considerations, you can take the limit. But in here, I want to reason in the continuous case without discretizing the problem and then going back to the continuous case. It's an informal mathematical derivation, but it works and it helps your intuition. So this is equal to, it's the following. So we have a product of three variables. Remember that these variables depend on time. And we can write the differential of the derivative of the first variable with respect to time, dx2, dx3, plus dx1, and then we have the differential of the derivative of x2 with respect to time, dx3, plus dx1, dx2, and then we have to multiply this by the differential of the derivative of x3 with respect to time. Now, the derivative of x1 with respect to time can also be written as the first component of the velocity. This would be the second component of the velocity, and this would be the third component of the velocity. So here we really have differentials of the velocity. So let me rewrite it. We have the differential of v1 here, and then in order to let the volume appear again, we can divide this differential by dx1, and then we multiply by dx1, and we also have to multiply by dx2 and dx3. And similarly, you have other terms. Here you can divide by, so you have dv2 times dx1, dx3, but you can divide dv2 by dx2, so that in here you have dx2, and therefore this volume element is the same as this one. Similarly, here you have dv3 times dx1, dx2, then you multiply by dx3, and then here we divide by dx3. So you can see that we can factor the volume element, and therefore here we have, informally we can write dv1 dx1 plus dv2 dx2 plus dv3 dx3 times the volume element. So we can write it as dv, where this v represents the volume, not the velocity. So it's dx1, dx2, dx3. And to be more rigorous and more formal, this would be actually partial derivatives, because each of these components of the velocity might depend in general on x1, x2, x3, all of them. And therefore these derivatives, these total derivatives, are actually partial derivatives. So this would be dv1 dx1 plus dv2 dx2 plus dv3 dx3, and this would be the divergence of the velocity times dv. So we can rewrite this result here in the following manner. We have the integral of df dt, partial derivative, plus the gradient of f times, dot product with the velocity from here. And then if we rewrite this integral together with the other one, in here we simply have f times the divergence of v, and then here we have dv. We can put these two together and rewrite everything like this. We have the divergence of the function, and then we have v. Now this is a well-known result that can be derived also in other manners, and I wanted to show you that even with just basic calculus intuition, you can derive what we have derived here. And let me also tell you before concluding the video that f, this f here, does not necessarily need to be a scalar function. It may also be a vector function, or a more complicated object if you want, a matrix or whatever, and this result will still hold, at least formally, written like this. If F were to be a vector, for example, here you have a vector and another vector. And it would be more convenient to rewrite this in index notation. But let me tell you that the divergence of a matrix, because a matrix can be thought of as a tensor product of two vectors. So in this case, here you should interpret this as a tensor product if f is a vector, is also a vector just like v. So this would be a matrix given by tensor product between two quantities, f and v. And the divergence of a matrix can be defined. This is just some intuition that I wanted to show you here.